In the last class, we have seen statistical modeling of multipath propagation in wireless channels. In this session, we will be studying the capacity of wireless channels. How to analyze the capacity of wireless channels. According to the syllabus, capacity of wireless channels, review of capacity of AWGN in the previous semester, not in the previous semester, before that, we have studied in analog and digital communication what is additive white Gaussian noise. This is the syllabus 2.3 capacity of wireless channels. We will begin this session by reviewing the capacity of a wireless communication system in AWGN channel, capacity of flat fading channel, what is ergodic capacity, capacity with outage, capacity with CSI-R. The derivations of the capacity formula is not required for your syllabus. Only the expressions, computations and significance is required. But you may get problems based on the capacity of a wireless channel. Although the derivation is not required, you may need to use these formulas to solve problems that might arise in your exams. Now let us consider a Gaussian random variable of mean mu and variance sigma square. This is represented using the notation n mu sigma square, where this means that it is a Gaussian random process and its mean is mu and variance is sigma square. In such a case, the probability density of such a Gaussian random variable may be denoted as f of x, fx of x, and will be given as fx of x is equal to 1 by root of 2 pi sigma square e raised to minus x minus mu the whole square by 2 sigma square. This is a probability density function of a Gaussian random variable with mean mu and variance sigma square. Standard Gaussian random variable. A Gaussian random variable with mean equal to 0, that is mu is 0 and the variance sigma square is equal to 1 is known as standard Gaussian random variable. So as discussed in the previous slide, this Gaussian random variable denoted by n01 as a probability density function, fx of x is equal to 1 by root 2 pi sigma square e raised to minus x square by 2. We have substituted 0 for mu. The cumulative distribution function of the standard Gaussian variable is given as q of t is equal to probability pt when x, capital X, the random variable, is greater than or equal to t, and that is given by integral t to infinity 1 by root of 2 pi sigma square e raised to minus x square by 2 dx. So consider a transmitted channel, consider a transmitted signal x of I passing through a channel and being received at the receiver's end. X of I, Y of I is the output at the receiver's end, will be the input signal, the transmitted signal plus the noise. Noise is the AWGN, additive white Gaussian noise, and this noise is added to the input signal to receive the output. The noise here is represented by N of I. So different types of fading in AWGN channel. We have seen this in the previous sections also. We have a fading channel. It could be a large scale fading or a small scale fading. Large scale fading consists of path loss and shadowing. Small scale fading consists of multipath fading, time variance. In multipath fading we have two types, frequency selective fading and flat fading. In time variance we have fast fading and slow fading. The wireless channel models for frequency selective, flat fading, slow fading and fast fading we have studied in the previous lecture. We have also studied multipath fading, different types of multipath propagation channel in the previous lectures. Definition for capacity of a channel. The capacity of a channel is defined as the maximum rate of communication for which arbitrarily small error probability can be achieved. As we have discussed in the previous lectures, one of the measures of capacity of a channel, any communication channel, is how less the probability of error can be. So whenever we design or whenever we model a channel, a wireless channel or any kind of communication channel, we should take probability of error into consideration. We have to bring probability of error to the least possible value so that our channel becomes highly reliable and will have good capacity. The AWGN channel, additive white Gaussian noise channel, is then used as a building block to study the capacity of wireless fading channels. In order to study the capacity of a wireless channel, we will consider this wireless channel to have an additive white Gaussian noise. I hope all of you remember what is additive white Gaussian noise. AWGN. The probability distribution function of the noise will be Gaussian. The noise is added to the input, that is why it is additive white Gaussian noise. We have colored Gaussian noise also. We have colored noises also. Here we will consider that the input signal is X of I and the noise N of I is added to the input signal to be received at the output, and it is called as Y of I. So we consider the noise to be additive in nature, white, Gaussian. It has a probability distribution function which is Gaussian. The signal to noise ratio is the next constraint that we should have in our mind while designing a wireless channel. Signal to noise ratio SNR of an AWGN channel is given by gamma. Gamma is equal to P by N naught B. The performance of communication system depends on the basic resources available in the channel. Two important basic resources are the bandwidth and power. The performance of a communication system depends on the basic resources available in the channel, bandwidth and power. So gamma is equal to P by N naught into B. The capacity of an AWGN channel is given by Shannon's well-known formula. Capacity C is equal to B log to the base 2 1 plus gamma bits per second, where gamma signal to noise ratio is given by P by N naught into B, where N naught by 2 is the power spectral density of the signal. As we have seen in the introduction, we don't need to study its derivation, but we need to study its formula. The capacity of an AWGN channel is given by Shannon's formula. C is equal to B log to the base 2 1 plus gamma bits per second gamma, the signal to noise ratio, is given by P by N naught into B, where P is the signal that is received, N naught by 2 is the power spectral density, and B stands for the bandwidth of the input signal. So as we have seen in the previous Shannon's formula, the capacity of the channel is proportional to the log of SNR, log of gamma. What it means? Higher the gamma, smaller effect of signal to noise ratio in the capacity. This is not directly proportional, it is proportional to the log of gamma. So when you get a question about the significance of signal to noise ratio in the capacity of a wireless channel, you may need to write this particular points as your answer. The capacity of the channel is proportional to the log of SNR. Higher the SNR, there is a smaller effect on the capacity of the channel. When the signal to noise ratio is low, the capacity increases linearly with the received power. Every 3 dB increase or doubling, the power doubles the capacity. When SNR is high, the capacity increases logarithmically with P. Every 3 dB increase in power only yields 1 additional bit per dimension. Increasing B yields a rapid increase in capacity because the increase in degrees of freedom more than compensates for the decrease in signal to noise ratio or gamma. All of you write down these points because there might be a question on the significance of signal to noise ratio in the capacity of any channel. So the question may come like this, that what is the significance of signal to noise ratio in the capacity of a wireless channel. In that case, all these points might be highly valid so that you can get full marks for the question. Similarly, when bandwidth B is large, the capacity is proportional to the total received power across the entire band. It is insensitive to the bandwidth, and increasing the bandwidth has a smaller impact on the capacity of the channel. On the other hand, the capacity is now linear in the received power, and increasing power has a significant effect. So from this, what we understand is that the capacity of a channel depends more on the power of the signal at the received end. Capacity of the channel depends more on the power of the received signal. As bandwidth increases, the capacity increases monotonically and reaches the asymptotic limit. When bandwidth approaches infinity, the capacity of the channel C is equal to limit B tends to infinity B into log to the base 2 1 plus gamma, where gamma is the signal to noise ratio, which is defined as P by N naught into B. So the capacity of a channel when the bandwidth is infinity is given by C is equal to P by N naught log to the base 2 E bits per second. When bandwidth tends to infinity, the capacity of the channel is given by C infinity is equal to P by N naught log to the base 2 E bits per second. You have to note that the capacity of the channel is given in terms of bits per second. This is the infinite bandwidth limit, the capacity of AWGN channel with only a power constraint but no limitation on bandwidth. It is seen that even if there is no bandwidth constraint, the capacity is finite. That means that the capacity of a channel is finite even when the bandwidth of the capacity C infinity is given by P by N naught log 2E, when the bandwidth B tends to infinity. This means that even if there is no bandwidth constraint, the capacity is finite. Discuss the significance of bandwidth to the capacity of the wireless channel. If a question arises like this, you can write that even if bandwidth tends to infinity or bandwidth is unlimited, you have unlimited bandwidth, you have the capacity to be a finite value. And also another important thing is that capacity is more connected with the power of the received signal. So let us now represent bandwidth and the capacity of the channel. Bandwidth is actually B here. B in megahertz and capacity in Mbps. Capacity is given by P by N naught log to the base 2E. When a question is asked on the significance of bandwidth and to the capacity of the channel, you need to explain by drawing this graph. Capacity of flat fading channels. In the previous session, we have seen what is a flat fading channel. Do you recall? A flat fading channel is a channel where the input signal bandwidth is less than the coherent bandwidth. The fading frequency is a function of mobile speed, Fd. Is equal to the velocity v by wavelength lambda. When the speed is high, fading frequency is also high. So that's why it's called as fast fading. Let us consider a transmitter with a signal W that is being encoded, and the encoded signal is x of I. After it passes through the wireless channel, it is received at the receiver end. The received signal is y of I, and what we receive at the end of the receiver is W caps. So in the channel we have the signal root Gi plus the additivized Gaussian noise N of I. So let us define what is an ergodic random process. A random process is said to be ergodic if all time averages of any sample function are equal to the corresponding ensemble averages or expectations. What is an ergodic random process? Now let us consider a discrete time channel with stationary and ergodic time varying gain given by root of G of I, where G of I is always greater than 0, greater than or could be equal to 0, and an AWGN channel with noise N of I. The channel power gain G of I follows a distribution Pg. For example, let us consider Rayleigh fading. P of G is exponential. We assume that G of I is independent of the channel input. The channel gain G of I can change at each time I, either as an independent or and identically distributed process or with some correlation over time. So what is G of I? G of I is the gain of the channel, time varying gain of the channel at different points of time. Okay. In a block fading channel, G of I is constant over a block length of T, after which time Gi changes to a new independent value based upon the distribution P of G. Let P bar denote the average transmit signal power with N0 by 2 power spectral density of the noise Ni, and B is the received signal bandwidth. In that case, the instantaneous received signal to noise ratio is given by gamma of I is equal to Pg cap I by N0 B, and this value Y of I, signal to noise ratio, will be between 0 to infinity, can be equal to 0, and its expected value over a overall time, gamma cap is equal to Pg cap by N0 B. Since this is a constant, power by N0 into B, the received power, the power spectral density, N0 by 2 is the power spectral density, B is the bandwidth. So this is a constant. The distribution Gi determines the distribution of signal to noise ratio and vice versa. The system model is also shown where an input message W is sent from the transmitter to the receiver which is reconstructed as W cap from the W cap of the transmitted message W from the received signal. The message is encoded into the code word X, which is transmitted over time varying channel X of I at time I. The channel gain G of I is also called as channel side information or CSI, and which changes during the transmission of the code word. So what is channel side information or CSI? The name itself gives you a lot of hint about what channel side information could be. Channel side information G of I is the gain of the wireless channel considering to a particular point of time. For a particular period of time, this will remain constant. Am I right? Yes or no? So what is channel side information? How the original signal, message signal that we call it here as W, or in other terms is X of I, gets distorted, it gets influenced by the wireless channel, is what we have been seeing. The capacity of this channel depends upon what is known about G of I at the transmitter and the receiver. The channel distribution information, CDI. The distribution of Gi is known to the transmitter and the receiver. Receiver CSI. The value of Gi is known to the receiver at time I, and both transmitter and the receiver know the distribution of GI. The transmitter and the receiver CSI. The value of GI is known to the transmitter and the receiver at time I, and both transmitter and the receiver know distribution of GI. Now this is where we will be studying three conditions. First condition is the distribution. First condition is the distribution GI is known to the transmitter and the receiver. Okay, the value and distribution, the value is known to the receiver, and both transmitter and receiver knows the distribution of GI. In the first case, we do not consider the value of GI, which is not known to the receiver or the transmitter. In the second case, we know the value of GI, okay, at the receiver. We know both the value and the distribution at the receiver. We know the distribution at the transmitter. In the third case, we know the value of GI and its distribution both at the transmission and the receiver's end. So let us consider the first case where the distribution of G of I, the channel side information, is known to the transmitter and the receiver. In this case, the channel gain distribution Pg, or equivalently the distribution of signal to noise ratio P of gamma, is known to the transmitter and the receiver. The capacity achieving input distribution and corresponding fading channel capacity under CDI are known for two specific modes of interest: IID, Rayline fading channels, and infinite state Markov channels, FS, MC. The second condition, receiver CSI, the value of GI is known to the receiver at time I, and both the transmitter and the receiver knows the distribution of GI. In this case, there are two channel capacity definitions that are relevant to the system design. Shannon capacity, which is also known as ergodic capacity, and capacity with outage. For Shannon capacity, the rate transmitted over the channel is constant. The transmitter cannot adapt its transmission strategy relative to channel state information, or CSI. In the coming slides, we'll derive both the equations for ergodic capacity and capacity with outage. And this is almost a very sure question in your university exams. Ergodic capacity. Capacity of a fading channel with receiver CSI for an average power constraint P is given as capacity. In the previous slide, we have seen two conditions. Okay, capacity with outage and ergodic capacity. Now we are going to derive the conditions where G of I is known. The value of G of I is known to the receiver, and both the transmitter and the receiver knows the distribution of G of I. The second instance in which you are going to derive the ergodic capacity. C is equal to 0 to infinity B log to the base 2 1 plus sigma probability distribution of sigma d sigma, where sigma is the signal to noise ratio of the channel. By studying mathematical inequality called as Jensen's inequality, we'll calculate the expected value of the channel capacity C, that is bandwidth B into log to the base 2 1 plus sigma, that is equal to integral B log to the base 2 1 plus sigma P of gamma d gamma, where gamma is the SNR. This value is less than B log to the base 2 1 plus E of gamma, which is equal to B log to the base 2 1 plus gamma bar, where gamma bar is the average signal to noise ratio of the channel. The Shannon capacity of a fading channel with receiver CSI only is less than the Shannon capacity of an AWGN channel with the same average SNR. If the receiver CSI is not perfect, capacity can be significantly decreased. So what do you mean by ergodic capacity? Ergodic capacity, under the condition where the value of GI is known to the receiver and the distribution of GI is known both to the transmitter and the receiver. So let us look into the explanation here. Let us consider the energy per bit EB by N0 with the spectral efficiency of the channel neta. Let this be the Shannon's limit. So the region in which R is less than the bandwidth limited region, power limited region. This is the capacity of flat fading channels. Now let us do a problem. We are going to do a problem, a solved problem that had come previously in your exams. Please note down the question. Consider a flat fading channel with IID. So consider a flat fading channel with IID channel root of GI, which can take three possible values. G1 is 0.05, the probability P1 is given as 0.1, for root G2 0.5, P2 is given as 0.5, for root G3 we have given P3 to be 0.4. We have introduced the values of, all of you listen very carefully, you may get problems based on this. The values of channel side information we have given three values and the probability of all these three values are given. The transmit power PT 10 megawatts, the noise power spectral density N0 by 2, we have N0 value being given as 10 raised to minus 9 watts per hertz, and the channel bandwidth 30 kilohertz. Now assume that the receiver has knowledge of instantaneous value of G, but the transmitter does not. Find the Shannon capacity of this channel and compare with the capacity of an AWGN channel with the same average gamma, signal to noise ratio. Have you understood the question? All of you, have you understood the question? So we have written down the given values. Power transmitted, we got signal to noise ratio. For the first case, PT G by N0 into B. Bandwidth is given, N0 is given, PT is given for G1. So you got 3, gamma 1, gamma 2 and gamma 3. The value of gamma 1, 0.79 dB. We got 0.833. We converted it into dB by using 10 log all power in terms of dB. Gamma 3 we got 25 dB, 19.2 dB. The first step towards solving this problem, we have calculated signal to noise ratio for the 3 points that were given, G1, G2 and G3 with their respective probabilities. We have already seen that signal to noise ratio gamma is given by P transmitted power into GI by N0 into B. So after we have calculated, now we are calculating the capacity C. We have seen that capacity C is nothing but summation of B into log to the base 2 1 plus gamma P gamma. We know the value of B. We have calculated gamma. Here we have three values 0 to 3, 0 to 2. The first one, second one and third one. You got the answer as 199.26 kbps. Next topic, capacity with outage. Capacity with outage is defined as the maximum rate that can be transmitted over a channel with an outage probability corresponding to the probability that the transmission cannot be decoded with eligible error probability. Capacity with outage applies to slowly varying channels where instantaneous signal to noise ratio is constant over a large number of transmissions and then changes to a new value based on fading distribution. Since the transmitter does not know the signal to noise ratio, it must fix the transmission rate independent of instantaneous values received. The transmitter fixes minimum signal to noise ratio and encodes for a data rate. C is given by C is equal to B into log to the base 2 1 plus gamma min. The transmitter fixes a minimum received signal to noise ratio and encodes for a data rate. The capacity C is given by C is equal to B log to the base 2 1 plus minimum required signal to noise ratio. The probability of outage then is given by P out is equal to probability that the signal to noise ratio is less than signal to noise ratio minimum. That means an outage occurs when we do not have minimum signal to noise ratio. The probability of outage is such that the probability of SNR is less than the minimum required signal to noise ratio. Understood? Understood what is probability of outage? All of you? Then we have another term called as outage capacity, C out. This is very important, this should be put in box. C out is equal to 1 minus P out B log to the base 2 1 plus gamma min. This is extremely important. So you need to underscore these things. It's very important. What is outage capacity? What is outage capacity? C out is given by 1 minus probability of outage. Probability of outage means probability that the signal to received signal to noise ratio is less than the required minimum signal to noise ratio into B log to the base 2 1 plus SNR min, gamma min. The average rate correctly received can be maximized by finding the minimum required SNR or equivalently the P out that maximizes the outage capacity. Graphically, the outage capacity versus the C out is given here. Sorry, outage capacity versus C by D, bandwidth. The third condition, transmitter and the receiver CSI. The value of GI is known both to the transmitter and the receiver, and its distribution is also known to the receiver. End of module 2. So these are the two problems that you have to do as assignment and submit to me. So these are some assignments, problems that can be practiced. With this, we conclude our sessions on wireless channels. End of module 2. Thank you all. Thank you very much for listening to this lecture.